Alright, now that we have a general idea on how to solve separable first-order differential equations, let's look at how to solve another type of first-order differential equation, the linear first-order differential equation. So now we're going to be solving linear first-order differential equations. If there's one thing that you can count on happening in differential equations, is that you're going to stick as many adjectives as in front of your differential equation noun as possible. So in this case, we're dealing with not only the first-order differential equations we were talking about last time, but specifically linear first-order differential equations. So now what does this even mean? So let's recall what our definition of the first-order differential equation in general was. It was some function f that takes x, y, and y prime, and it equals 0. Y prime is just dy dx. Well, when we talk about first-order differential equations that are linear, we specifically refer to a differential equation which can be put in the form dy dx, so that first derivative, plus, and then what is important about it being linear is that coefficients never contain the dependent variable itself. So in this case, the dependent variable is y. So the coefficient can never contain y or y prime. So we're going to have a function purely of x, which I'm going to call p of x. And then this is going to be y times y. And this is going to be, again, a different function purely of x, q of x. If your differential equation is in this form, it is a linear first-order differential equation. First order because we have this dy dx here. Linear because we only have functions of x multiplying into here. I can also rewrite this as y prime. Now I might be wondering, why is this coefficient here 1? Well, you could conceivably write this as another function, g of x times y prime, plus p of x times y equals q of x. But you could just as easily not write this g of x and say, all right, we're going to divide through by g of x, and then your p of x is going to be p of x divided by g of x, q of x divided by g of x. It's going to be the same thing because you have still only functions of x, and that's all we care about. Now, if we have this linear first-order differential equation, how do we solve it? That's the next important question. Well, the way that we're going to solve this stems from an observation about its form. If we recall back to the product rule from differential calculus, the product rule states that if you take the derivative of some function of x times some other function of x, this is going to equal the derivative of the first function times the second function plus the first function unchanged times the derivative of the second function. This is the product rule. And it looks eerily similar to the left side of this equation, because what we're seeing is here we have a y prime and a y. So it's almost like what we have is a product rule where f of x is y, so we're having the derivative of y, and then not the derivative of y. And in that case, then p of x would have to be g prime of x, and this 1 would have to be g of x. Now that obviously won't work, but the observation that it could almost be the product rule is what might lead someone to thinking, hey, is there anything we can do to this equation to make it conform to the product rule? What I mean by that is there any function, and we typically use the function mu, which is Greek letter long-tailed u. Is there any function mu of x, magic function mu of x, such that if we were to multiply mu of x by both sides of the equation, so we have mu of x y prime plus mu of x times p of x times y equals mu of x times q of x. Is there any magical function, mu of x, such that if we multiply into both sides of the equation, the left-hand side, this side, becomes the product rule. Does such a function exist? Well, let's think about what properties this function would have to have if it was to complete the product rule on the left-hand side of the equation. Well, if we're assuming that we're trying to get this into the form of dx of mu of x times y, if we're going to get this, then the expansion of this, just using the product rule again, is going to be mu of x times y prime plus the derivative of mu of x, mu prime of x, times y. And we can see we're very close to getting this. If we look at the first term, we have correctly mu of x times y prime, mu of x times y prime. So the first term, it's all good. Any mu of x will satisfy the first term. And now if we look at the second term, we have this y, and y. So that's the same. That's fine. The only issue is this mu prime of x must equal mu of x times p of x. But luckily, this mu of x is an arbitrary function, so we should be able to write this down as a condition that mu of x must satisfy, and then solve for mu of x. So if we do that, what we'll get is that we're trying to solve for mu of x, where mu prime of x equals mu of x times p of x. And let's think back to separable differential equations. We can rewrite mu prime of x as the following. We can rewrite it as d mu dx. And now this is looking an awful lot like a separable differential equation, because it is. We have the derivative of mu with respect to x equals a function of this mu, and then this, we have mu as a function of x only, p as a function of x only, so we can think about this as mu of x times p of x as being yet another function of x only, so this is like another only x function, and then we could think of this empty space here as being some quite lousy function of just y, being maybe just 1. So we have a multiplication of a function of purely x, function of purely y. Let's think of what this might be when we solve it. We're going to get that if we multiply out the dx, that d mu equals mu of x p of x times dx. And in this form, we can simply take the integrals on both sides. And what will we be left with? But that mu of x, this function that we're trying to solve for, is going to equal the integral of, looks like I have made a slight mistake, which is that I was looking at this as mu of x as a function, and actually we want to get this to the d mu side because it is mu, and I was making a mistake by thinking of it too much as a, so okay, let's backtrack a little bit here. So let's delete some stuff here. Sorry of this issue. Okay, so what we can write this as is that, so let's get this back. Okay, so mu prime, this is going to equal mu times p. And we want to get this mu to, using again the separation of variables, we're going to get this mu to the mu prime side. So we're going to divide by mu. Alright, so we're going to get, so we want to get mu onto the mu side. Just like if we imagined that mu was y, then we would have that y prime equals y times, and then maybe some function of x. So p of x. We want to get the y on the y prime side. That's where it's getting messed up. Even though mu is a function of x, it's still mu, so we want to get it onto the d mu side. So you always make mistakes in mathematics, even the best and worst of us. So if we get the mu onto the mu prime side, what we're left with is 1 divided by mu d mu equals p dx. So I went through the separation of variables pretty quickly, but I multiplied by the dx and I divided by the mu. Now if we take the integral of this correct expression, what we're going to get is we have on the left side the integral of 1 divided by mu is going to be the natural log of the absolute value of mu. And again, we're going to save up our plus c for the very end. And we're going to have equals, and the integral of p of x dx. We're not actually sure what that is because p of x could be anything. So we're just going to leave that in the form of the integral of p of x dx. But we can still go ahead and add our c to the equation. Now, if we think about raising both sides to the power of e, well, not raising, but putting e to the power of both sides, then we'll finally get that the absolute value of mu, which again, as we know, we can remove and then increase the boundaries on c, that mu of x, this what's called an integrating factor for this equation, is going to make it into the product rule. Mu of x equals, and I'm going to do this fewer colors, is the integral, we should say e to the integral of p of x dx times c. Now, there's something important to notice here, which is that this c, again, not equal to 0, but how useful is this c? And these are different c's, by the way, so this is really c1 and c2. How useful is this c? Because if we multiplied through by mu of x equals c2 e to the integral of p of x dx into this equation, well, let's actually do it. Let's just do it up here. What are we going to get? We're going to get that c2 times e to the integral of p of x dx times y prime plus c2 e to the integral of p of x dx times the actual function p of x y equals, and I'm just going to leave this as mu of x times q because I don't think we actually have enough room to finish it if I expanded it out there. Now, notice what's happening here. We have this first c2 and this second c2. If we felt like it, which we do, we can just factor this out to get c2 times, and now we do the derivative, times the derivative of e to the integral of p of x dx y, which, and notice this integrating factor does work, because if you were to evaluate this derivative on your own, you would get, first, take the derivative of y, that gets you e to the integral of blah times y prime. Second, take the integral of this, which, and it's almost ingenious how math came up with this solution, e to the anything stays that way, but then we apply the chain rule, and fundamental theorem of calculus, derivative of an integral is that function itself, which is why this side turns into what we need it to be. So we get this, and then we'll get this second term. It does work, but it's almost annoying that we're carrying this second c because it doesn't actually change anything. If you multiply an equation by a constant that is just for this function, any constant would work, right? Any c2 would get this product form, this product rule form, which is what we're going for. If any c2 works, why would we use any c2 but the simplest one, right? Why would we say 7 times the derivative, or 89.12 times the derivative? Why would we use any number but the simplest, which would be 1? So through that line of logic, we can say, okay, even though we really do have any constant that we want here, we can, for the sake of simplicity, just say that this c2, so we just say that c2, I guess I'll write it in orange, c2 equals 1, to keep things simple. And by setting c2 equal to 1, the final value for our equation becomes, all right, let's write this out in a nice color, that the derivative with respect to x of e to the integral of p of x dx times y equals e to the integral of p of x dx, just expanding out mu here, times q of x. And if we take the integral of both sides and divide by this e to the integral of p of x dx, we'll be left with an expression for just y. But on a video that's just going through the theory of how to solve the linear first order differential equations, this integrating factor, which is what it's called, this integrating factor, is the key. And I would encourage you to not memorize this formula. If you were to memorize this formula, it'd almost be a waste of brain space. Just try to remember, all right, we have something really close to the product rule. Let's get it to be the product rule. What function makes that happen? Well, you could either solve it or remember it, doesn't really matter. But try to get into the product rule, multiply by e to the integral of p x dx, and then you get this nice form that's much easier to solve. In the next video, I'm going to do a few example problems of solving our linear first order differential equations. See you then.